Hi, I'm Amy Bodette from the Alt Store. Thank you for watching the fourth of our video series on designing an off-grid solar system. This video will explain how to size a charge controller for your off-grid system. We'll discuss the two major types of charge controllers and figure out how to select the right size for your system. Our previous videos helped us determine how much power we needed to make, what size battery bank was needed to store it, and what solar panels were needed to generate that power. Now we'll figure out what charge controller is needed to manage that power. We're getting closer to completing the system. We've figured out the house loads, done the batteries and panels, and now let's do the charge controller. We've got another video that goes into great detail of the difference between a PWM and an MPPT charge controller, so I'm not going to repeat much of that. The short version is, charge controllers are available with two different technologies, PWM and MPPT. How they perform in a system are very different from each other. An MPPT charge controller is more expensive than a PWM and is often worth it to pay the extra money. PWM charge controllers operate by making a connection directly from the solar array to the battery bank. During bulk charging, when there's a continuous connection from the array to the battery bank, the array output voltage is pulled down to the battery voltage. As the battery charges, the voltage of the battery rises, so the voltage output of the solar panel rises as well, using more of the available solar power as it charges. As a result, you need to make sure that you match the nominal voltage of the solar array with the voltage of the battery bank. A 12-volt solar panel can charge a 12-volt battery. That's nominal. A 24-volt solar array is needed for a 24-volt battery bank, and 48-volt array is needed for a 48-volt bank when using PWM. MPPT charge controllers measures the VMP voltage of the panel and down converts the PV voltage to the battery voltage. Because power in equals power out, when the voltage is dropped to match the battery bank, the current is raised, so you're using more of the available power from the panel. So you can use a higher voltage solar array than battery, like the nominal 20-volt grid-tied panels that are more readily available. With a 20-volt panel, you can charge a 12-volt battery bank, or 2 in series can charge a 24-volt bank, and 3 in series can charge a 48-volt bank. This opens up a whole wide range of panels that now can be used for your off-grid system. To determine what the specs are for a solar panel, you can look at its data sheet or the label on the back of the panel. When sizing a charge controller, the two numbers you're most interested in are open circuit voltage, or VOC, and short circuit current, or ISC. These are the volts and amps the panel outputs when it's not connected to anything pulling it down. You keep hearing me talk about nominal voltage. Nominal voltage is a way to categorize battery-based solar equipment. Because a higher voltage is required to charge a battery, nominal voltages are used to help see what equipment goes with what. So a nominal 12-volt panel, which actually has a VOC voltage of around 22 volts, plus or minus a volt or two, and a VMP of around 17 volts. And if you count the number of cells, or silicon squares on the front, it'll likely have 36 cells. Likewise, a panel that was designed to charge a 24-volt battery bank will have a VOC of around 44 volts and VMP of around 36 volts. Counting the cells will come up with 72, twice as many as a 12-volt panel. If you wire two 24-volt panels in series, or 4 12-volt panels in series, you can charge a 48-volt battery bank. This was all well and good for battery-based systems, but then along came grid-tied systems, and 12, 24, and 48 volts became pretty meaningless. So the industry sort of standardized on 60-cell or 20-volt nominal panels. Alone, they're too big to charge a 12-volt battery and too small to charge a 24-volt battery. An MPPT charge controller solved that by reducing the voltage down to the required range, and in doing so, increasing the current output so you're not losing power. So let's start with sizing a charge controller with matching panels and batteries. This can be done with a PWM charge controller. Our first example is going to be one string of panels. We check the label or data sheet and confirm that with a VOC of 22.1 volts, that it is a nominal 12-volt panel, and that the ISC is 8.68. We then multiply the ISC by the number of parallel strings, 1, and multiply it by NEC's safety factor of 1.25 to get 10.85 amps minimum charge controller size. Great, I'll round that up to a nice 15 amp Morningstar ProStar 15M with a meter. Now let's try it with 4 parallel strings of the same 140 watt panel. Notice I'm not talking about how many panels are in each string in series because I'm using a PWM charge controller. I know that I'm using the right number to match the voltage of my battery bank. So I've got 1 panel for 12 volts, 2 in series for 24 volts, and 4 in series for a 48 volt battery bank. So here we go with 4 parallel strings. 4 strings times short circuit current times NEC's 1.25 equals 43.4 amps. So I'm going to round up to a nice Morningstar TriStar 45 amp charge controller. Now let's get into MPPT charge controller. If you're using the same nominal voltage panels as battery bank, the math is exactly the same as what we just did for the PWM. An MPPT charge controller can manage the same or higher nominal voltage panels as batteries. There are some boost charge controllers that can take a lower voltage panel and boost it up to the correct voltage to charge a higher voltage battery bank. These are generally designed to take a single panel to charge a 36 volt or 48 volt golf cart. However, most charge controllers need the nominal voltage to be equal to or higher than the battery bank. Because watts equals volts times amps, and the watts are constant, if the voltage drops, the current goes up. For example, if you have a 200 watt panel with a voltage of 40 volts and a current of 5 amps, if the voltage drops in half to 20 volts, the current doubles to 10 amps. The 200 watts remains the same. When the voltage of the array is higher than the battery, the charge controller will reduce the output voltage to charge the batteries and increase the current output. A lot of MPPT charge controllers can handle a higher input voltage than a nominal 48 volts. This allows you to use several solar panels in series to increase the voltage in the line going from the panels outside to the charge controller and batteries inside. When you see the max voltage rating of a charge controller, that is the highest VOC voltage of the string of panels plus a temperature duration for the coldest temperature the panels will be exposed to during sunlight hours. So if it ever gets to minus 20 degrees Fahrenheit during a cold winter morning, like it does here in New England, you need to multiply the VOC of the panel by 1.21 to determine the highest voltage the panels may potentially put into the charge controller. So to figure out how many panels you can do in series for a charge controller that's rated for 150 volts, you multiply the VOC of the panel by the number of panels in series by the temperature duration factor. If we try putting 4 nominal 20 volt panels with a VOC of 39.4 volts in series, when we multiply times the 4 panels, we are already over the 150 volt limit, even without the temperature correction. So if we drop it down to 3 in series, times 39.4 volts, times 1.21 temperature correction, we're just under at 143 volts. We're within the acceptable voltage range. So let's look at what happens when we put a string of 3 240 watt panels in series and send it into a 12 volt battery bank through our MPPT charge controller. We have 240 watt panels times 3, which gives us 720 watts. Next, we take that 720 watts divided by a 12 volt battery bank, which equals 60 amps out of the charge controller. Okay, so I know I need a charge controller that's rated to handle at least 60 amps. Outback makes a great FlexMax 60. I can see if that'll work for me. The next step is to confirm with the specs of that charge controller you want to use to see if it can handle the full wattage of the array at that battery voltage. I see in the specs for the 12 volt system, it can handle up to 750 watts. Well, 720 watts is less than 750 watts, so we are good to go. So let's use the off-grid example we've been using throughout this video series to figure out what equipment we need. Looking back through our list of steps, We have everything we need to calculate the charge controller needed from our previous videos. We had decided to do a 48-volt battery bank, and we need an array of at least 1168 watts. First, let's do a PWM charge controller. We know we need at least 1168 watts of solar. We also know we need to have the nominal voltage of an array that's equal to 48-volt battery bank. So we will use two 24-volt panels in series to equal 48 volts. If we use the SolarWorld 315-watt panels, 1168 watts divided by 315 watts equals 3.7. So we need 4 of those panels. So we'll have 2 parallel strings of 2 in series. To figure out what size charge controller we need, we take those 2 strings times 9.19 amps short circuit current times that safety factor of 1.25 equals 22.9 amps. So we can round up to a 25 or even 30 amp charge controller, depending on which model we like. For instance, the Blue Sky Energy Sun Charger. Now let's do an MPPT charge controller. We know we need at least 1168 watts of solar. We also know that we need to have a nominal voltage of the array equal to or greater than the 48-volt nominal battery bank. So if we wanted to use nominal 20-volt panels, traditionally used in grid-tied, we would have to use 3 in series to get at least 48 volts nominal. If we use the Kyocera 260-watt panels, 1168 watts divided by 260 watts equals 4.5. But we know that we need to do strings of 3, so we have to use a number divisible by 3. So we round up to 6 panels. So we'll have 2 parallel strings of 3 in series. So let's look at what happens when we take our 2 parallel strings of Kyocera 260-watt panels in series and send it into a 48-volt battery bank through our MPPT charge controller. The wattage of each panel is 260 watts, and we have 6 of them for a total of 1,560 watts. Next, we take that 1,560 watts divided by a 48-volt battery bank equals 32.5 amps out. Okay, I can probably use a Morningstar TriStar 45. Let's double check to see if the specs agree. So this is interesting. Even though our math says we need at least 32.5 amp output, the Morningstar specs are saying that their 30 amp charge controller can handle up to 1,600 watts with a 48-volt battery bank. That's because the MPPT charge controllers are designed to current limit their output. Even if I'm putting enough power in to generate 32 amps out, the charge controller will limit it to 30 amps. So I have a choice. I can slightly undersize the charge controller and get the TriStar 30, knowing that on occasion it may clip the output a little, or I can move up to the TriStar 45 charge controller, which will output the full 32.5 amps. Either one is fine. I just need to decide if I want to pay a little more for a bigger charge controller that will not limit the output, or if the occasional loss of 2 amps is adequate. With a 45 amp charge controller, I also have room for additional panels in the future if I want to expand. Being able to handle up to 2,400 watts, I could add a third string of 3 panels in the future, bringing me up to 9 panels and 2,340 watts. You may be adding additional loads in the future, so it may benefit you to have some wiggle room for growth. Well, that's it for this. You can go to our website to check out our selection of PWM and MPPT charge controllers. Watch the final video in this series on how to select the inverter using the numbers we've come up with. Also watch more of our various video series on our website. And we've got a team of highly trained technical sales reps available to help you plan your system. Give us a call. Thanks so much.